to talk today about seafloor spreading. So we're in section 2 in chapter 11 titled Seafloor Spreading. In the 1950s, 1960s, there was a geophysicist that actually worked for the Navy. His name was Harry Hess, and he set out on a mission to essentially map the ocean floor. Up until that time, no one really thought the ocean floor had anything on it. They just kind of thought it was flat, plain, and boring. And as Hess went out in these naval ships and started getting data back, they started noticing that, hey, it's really a little bit more exciting than we actually thought up until that point. So naval maps showed undersea mountain chains that formed a continuous chain down the centers of the ocean floor. And Hess wondered if the new ocean floor was actually created at these places that they called mid-ocean ridges. So Hess's idea, seafloor spreading, was that as new seafloor is made at those mid-ocean ridges, the continents are actually pushed away. So that would mean that the newest oceanic crust would be along the mid-ocean ridge there, and then the oldest would be near the continents. So he called his hypothesis seafloor spreading. And he had evidence for it, just like any other good scientist would have. So his evidence was that there was matching magnetic patterns in the rocks on either side of the mid-ocean ridges, and that there's actually matching age of rocks on either side of the mid-ocean ridges as well. I'm going to show you a picture right now what that actually means. So if you look here, you can see how we have the different colored rocks on either side of the mid-ocean ridge. They're kind of showing like a red color, a brown color, a different color tan in there. When magma or lava comes up from the ocean floor, if it contains iron, as we know, we find inside the earth frequently, those iron minerals will actually line up with Earth's magnetic field at the time, and you can see patterns on either side. So we will see matching patterns, almost like, think of this as a mirror image on either side, the middle being where the mid-ocean ridge is. So you have that, so you have this matching magnetic patterns on either side, and then we also have the age of the rock. So near the mid-ocean ridge, we find the youngest rocks, and as you work your way out, once again, that matching pattern, you're gonna have the oldest rocks on the outside. We have two different kinds of lithospheric plates, oceanic and continental. Continental plates are made up primarily of the rocks andesite and granite, and then oceanic plates are primarily made up of the rock basalt. A big difference between the two that you need to remember is that continental plates are less dense and oceanic plates are more dense. Remember, anytime we get two things coming together, one is more dense than the other, it can kind of already give you the clue as to what's going to happen, let's say, if these two tectonic plates meet with each other. So what moves these lithospheric plates? We believe there's convection cells in Earth's lower mantle that drive those lithospheric plates to move. So imagine, just like any other thing we've talked about in earth science, where you have warm things rising, cool things sinking, the same thing's going to happen with material inside the Earth. You're going to have that warm mantle material rising, cooler mantle material, once it gets up to the surface, sinking. When you have that movement of that really thick magma inside the Earth, it's going to undoubtedly drag what's on top of it. And if we have these broken plates, lithospheric plates on the top, then it's going to set up a situation where they can easily be moved. So cooling makes the nearby material denser. It sinks deep into the lower mantle. This is another picture, really good, showing you those convection cells in Earth's crust. If one of them actually if one of them gets pushed underneath another one, we call that particular process subduction, sub meaning below, so subduction, sinking process of tectonic plates into the mantle. Hotspots and island chains. Here's another feature that we see happening on Earth's surface. So a hotspot is a single hot rising mantle plume in Earth's crust. If the eruption is strong and it lasts long enough, the volcanic eruption may form an island on the plate. And the picture here should look familiar to you. This is Hawaii. This is a great example. It's probably the #1 example of a hotspot or an island chain. We believe there is a hotspot underneath Hawaii. Actually, the island of Hawaii, are a little bit off that right now. And over the last 6 million years or so, it's been putting up magma in this one location and then moving. When we look at the age of rocks and compare them on the different islands, Hawaii actually has the youngest rocks, and then the island of Kauai is going to have the oldest rocks all the way up to 6 million years. You can see a pattern here too when we look at this. Maui, less than 1 million years, Molokai 1.3 to 1.8. So you can really see they get older as you move down the ocean chain there. And this picture is a really nice three-dimensional picture just showing you here that after the island forms, the movement of the plate, because we know the Pacific plate is moving in that direction, the land is there, it was created, And the plate's moving, so it's just going to carry it right along with it as it moves.